Welcome back to The Explainer. Let's jump right into some fascinating new research exploring a huge bottleneck in our technological future, the quantum workforce. I mean, we hear about quantum computing, quantum sensors, the whole shebang constantly in the news. But there's a hidden issue that could literally stop all this progress in its tracks. And actually, it's not a hardware problem at all. It's a human one. Today, we're unpacking an eye-opening study by Tunde Kushimo, Bradley Holt, and Mohammed Talal. They took a really hard look at the U.S. higher education system to see, are we actually preparing students for the quantum jobs of tomorrow?
It's a simple question, right? But the answer has massive implications. Quantum systems are rapidly transitioning, like right now, from highly experimental research prototypes into deployable commercial technologies. We're moving from just proving quantum mechanics works to actually building stuff with it. So, we've got to ask a super pragmatic question. Do the people supposed to build and maintain these systems actually have the right skills? Well, the data suggests we might be due for a serious reality check.
To make sense of all this, we're going to break this explainer down into 5 quick sections. The Quantum Workforce Challenge, analyzing master's curricula, theory versus applied skills, bridging the industry gap, and finally, the future of quantum education.
All right, let's start with Section 1, the Quantum Workforce Challenge, moving out of the lab and into reality.
So the researchers point out that quantum tech, it's not just some niche academic pursuit anymore. It's recognized as a top-tier, absolutely crucial strategic priority for the United States. Economic competitiveness, national security, technological innovation, the stakes literally could not be higher. Whoever leads in quantum holds a massive advantage, which means the talent pipeline supporting this whole industry has to be completely rock solid.
And you can really see the paradigm shift happening here. In the past, the focus required a workforce of mostly PhD-level theoretical physicists locked away in isolated labs. But now, as we shift to deployable technologies, the spotlight is squarely on workforce preparedness at the master's degree level. You don't just need physicists anymore. You need engineers, project managers, and software developers who can take these concepts and build scalable, reliable products.
Which brings us to Section 2, analyzing master's curricula, mapping higher education to industry needs.
This study is honestly a bit like a detective story. The researchers followed 3 really methodical steps. Step 1, they analyzed the primary U.S. master's programs in quantum science. Step 2, they didn't just read course titles, they mapped the actual course offerings using a highly structured coding framework. And Step 3, they took those aggregated profiles and compared them directly against what the quantum industry says it actually needs.
And here's the real kicker. During that mapping phase, they rigorously analyzed all these courses across exactly 6 specific quantum-relevant skill categories. We're talking things like quantum algorithms, hardware interfacing, and error correction. By bucketing the curricula this way, they didn't have to guess. They generated precise, hard data on exactly what technical skills universities are prioritizing.
Okay, let's dive into Section 3, theory versus applied skills, the expectation versus reality gap.
So here is where we see a massive mismatch in the ecosystem. In academia, the reality is this super strong emphasis on quantum theory. Universities are fantastic at teaching the math and the physics behind it all. But the industry? They have a huge demand for technical, applied, and professional skills. Basically, universities are churning out quantum philosophers, but the industry is practically begging for hands-on quantum engineers. They want to know if you can program a quantum controller, not just calculate a state on a whiteboard. Digging a bit deeper, the research shows that while the theory is uniformly strong everywhere, everything else is kind of a lottery. There's substantial variability across programs when it comes to technical skills, applied learning opportunities like lab work, and professional development. So depending on where you get your master's, you might graduate totally ready for a corporate lab, or you might graduate with a head full of theory and absolutely no clue how to apply it in the real world.
Let's move to Section 4, bridging the industry gap, identifying the missing links.
Looking at this breakdown, the disconnect becomes super obvious. Sure, the alignment on quantum theory is there, but look at these persistent gaps. We're talking basic workforce readiness, cross-disciplinary integration, because quantum requires blending physics with computer science and engineering, and adapting to emerging technological demands. The field is just moving so fast that static courses are really struggling to keep up with what companies are inventing week to week.
Now, why is this specific study such a game changer? Well, the authors point out that before this, hardly anyone had actually integrated a systematic curriculum analysis directly with documented industry expectations. People complained, sure, but almost no one mapped it out with empirical data like this. It takes the conversation from anecdotal hiring complaints straight into actionable facts.
Finally, Section 5, The Future of Quantum Education, a Blueprint for Redesign.
The beauty of this research is that it doesn't just point out the flaws and leave us hanging. It gives us a scalable framework. We're talking evidence-based insights for curriculum design, shaping workforce policy, and supporting the continued development of the whole U.S. quantum ecosystem. If we could just align the classroom with the clean room, the potential here is absolutely limitless.
To wrap up this explainer, I want to leave you with a pretty provocative question. As quantum innovation continues to accelerate at this breakneck pace, can our traditional educational systems evolve fast enough to build the workforce of tomorrow? We've clearly got the theory down, but the practical application needs work. The blueprint for a fix is out there now. The only question is, will we use it in time? Thanks so much for joining me on The Explainer. Keep questioning, keep learning, and I'll catch you next time.